America does possess now the technologies to attain very significant improvements in the effectiveness of our conventional non-nuclear forces. Proceeding boldly with these new technologies, we can significantly reduce any incentive that the Soviet Union may have to threaten attack against the United States or its allies. As we pursue our goal of defensive technologies, we recognize that our allies rely upon our strategic offensive power to deter attacks against them. Their vital interests and ours are inextricably linked. Their safety and ours are one, and no change in technology can or will alter that reality. We must and shall continue to honor our commitments. I clearly recognize that defensive systems have limitations and raise certain problems and ambiguities. If paired with offensive systems, they can be viewed as fostering an aggressive policy, and no one wants that. But with these considerations firmly in mind, I call upon the scientific community in our country, those who gave us nuclear weapons, to turn their great talents now to the cause of mankind and world peace, to give us the means of rendering these nuclear weapons impotent and obsolete. Tonight, consistent with our obligations under the ABM Treaty and recognizing the need for closer consultation with our allies, I'm taking an important first step. I am directing a comprehensive and intensive effort to define a long-term research and development program to begin to achieve our ultimate goal of eliminating the threat posed by strategic nuclear missiles. This could pave the way for arms control measures to eliminate the weapons themselves. We seek neither military superiority nor political advantage. Our only purpose, one all people share, is to search for ways to reduce the danger of nuclear war. My fellow Americans, tonight we're launching an effort which holds the promise of changing the course of human history. There will be risks, and results take time, but I believe we can do it. As we cross this threshold, I ask for your prayers and your support. Thank you, good night, and God bless you.
All right, hello everybody. Welcome to the Land Commander Gulf War III update. However, today we're gonna skip Gulf War III, and we're gonna do an in-depth look at ballistic missile defense. I suspect that this will likely be the first in at least 2 videos, but maybe 3, because the reality is what we're really talking about is air defense in its totality, which has many different components and facets, everything from ballistic missiles that are going to travel out of the atmosphere and re-enter to their target, to hypersonic glide vehicles that are going to go up to the edge of the atmosphere and then tip down and go like this, to low-flying, slow cruise missiles, to FPV drones, basically anything between the surface of the Earth and outer space and beyond can fall under the category of air defense. But we're gonna start specifically with ballistic missile defense. And part of why I wanted to do this topic is with the ongoing Gulf War III, interceptors are a big topic. I mean, every day that's big in the media discussing, are there enough interceptors? Are our nations running out? Are interceptors effective? So it's a big topic, and we've touched on it some in these videos. I also want to touch on it because a friend of mine specifically asked if I would be interested in doing a more in-depth look at this stuff. And I thought, well, give the people what they want. So we're going to talk about ballistic missile defense today. The other reason I want to start with this facet of air defense is that ballistic missile defense, in order to successfully intercept a ballistic missile that's traveling at just crazy velocity, leaving the atmosphere, coming back in, to successfully intercept something like that is very difficult. There are many steps, lots of doctrine, lots of pieces of equipment that all have to come together to make that intercept work. And the concepts, principles, doctrines, kinds of equipment, in broad terms, if you understand how ballistic missile defense works, you can broadly understand sort of how all air defense works. And so we'll use this video as the starting point, give you some concepts to work with, and then we can get into more specific kinds of air defense beyond ballistic missile defense in subsequent videos. So here we go. We're going to start. This is a picture of a amphibious assault ship firing an anti-ballistic missile off its deck. It's probably an SM-3. SM stands for Standard Missile. The United States Navy, I think there's 6 versions of the SM series that exist, SM-1 all the way through SM-6. The primary ones the United States uses are the SM-2, 3, and 6. The SM-3 and I believe the SM-6 have the capability to do out-of-atmosphere interceptions. And so there they are firing one off of the back of an amphibious assault ship in a test to see if that was something that would be viable. Usually they're shot off things like Arleigh Burke destroyers. But if you can get a vertical launch system or something equivalent on virtually anything, you can launch one of these missiles. Anyway, I think it's kind of a cool picture. And yeah, with that, let's keep moving. Oops, better get the PowerPoint actually up. So let's start with this. What is ballistic missile defense? Ballistic missile defense is the uses of systems, technologies, and doctrines to detect, identify, track, discriminate, and destroy incoming ballistic missiles. And there's a variety of ways that you can do that. We'll talk about that. BMD, ballistic missile defense, was originally conceived, I mean, admittedly, ever since humans started hucking things at each other, you know, rocks, arrows, spears, there has been a push to find a way to knock them out of the air before they get you. But in terms of what we're talking about, the idea really came about, you know, at the end of World War II, going into the Cold War, and then it really took on prominence as intercontinental ballistic missiles, ICBMs, meaning missiles that had the capability of launching from, say, a missile silo in Montana and traveling all the way to Moscow, or vice versa. So long-range ballistic missiles, very long range. You know, as those were coming into the fold on both sides, there became an increased push to see if we could shoot them down. And there's a lot of history in the early decades of ballistic missile defense in the 50s, 60s, and 70s. That's pretty interesting. We're not really going to touch on a lot of that, primarily because the modern ideas about BMD really came into fruition in the 1980s under the Reagan administration. And a lot of that just has to do with a combination of factors, not the least of which is that technology had gotten to the point where certain things now seemed feasible, like shooting a missile from space, seemed feasible. They weren't necessarily feasible, they seemed feasible for the first time in history. And Reagan really was really infatuated with the idea of being able to SWAT down missiles. He really found the concept of mutually assured destruction to be totally abhorrent. For all of Reagan's flaws, I will say this, he actually did seem to be a pretty true nuclear abolitionist and really did want to find a way to get the world out from under the cloud of potential nuclear destruction all the time. Not saying the way he went about it was perfect, but I do think we haven't had a lot of presidents who seemed as into that idea as he did. And ballistic missile defense under him really came into fruition in its modern form then. So we're gonna really start with the history there. And down here you've got a nice little diagram that kind of just gives you a rough sense of how ballistic missile intercepts work. You know, the missile arcs up, leaves the atmosphere, comes back down. Excuse me, it goes this way actually. And you know, you can see all the different things that have to happen: detect, cue, track, classify, fire control, intercept, update, kill, you know, all of these things, right? And we'll get more into detail, but keep this picture in mind as we're moving forward. And keep in mind, you know, the arc of the missile we're talking about, keep in mind the curvature of the Earth, and keep in mind these different pieces of equipment that all have to come together to eventually intercept a missile. Okay, moving on. Here we go, Strategic Defense Initiative, Department of Defense. There's Reagan in his famous 1983 speech where he announced the creation of the SDI, which more colloquially was known as Star Wars. And it was a big push to get a combination of ground and space-based assets developed and fielded in sufficient quantity with sufficient ability to intercept incoming missiles to render the nuclear arsenals of the Soviet Union irrelevant, right? Make it so that no matter how many missiles they had and if they did want to shoot first, that just could not happen. Okay. We understand a little bit about what ballistic missile defense is. We understand kind of when it began. Now let's actually talk about what a ballistic missile is. So a ballistic missile is a type of missile, a projectile, that travels along a ballistic arc. So it means it's not going to travel a straight line to its target. It's going to arc up, and then at the apex of it begin arcing down and gain tremendous velocity on its downward trajectory. The flight path or the flight pattern of a ballistic missile is broken down into 3 phases. You have the boost phase, so that's the first phase, right? And that's from point of launch to the point at which the ballistic missile's engine cuts out and usually separates. And that's a key thing too with ballistic missiles, is that they are not powered through the entirety of their flight. They have a short window at the beginning, the boost phase, where all of the kinetic energy that's going to be imparted to it chemically through a rocket motor is going to be imparted, and then it will travel the rest of its way under that momentum combined with whatever momentum it's going to pick up from gravity as it comes back into the atmosphere. It's like a bullet. You know, you shoot a bullet, right? You pull the trigger, and the pin hits the back of the bullet. It ignites the powder. That powder burns very fast, and then shoots that bullet out down the barrel, and then out the front. All of the energy that you as the shooter and the gun and the powder is going to impart into that bullet occurs in that very short time period. And then the rest of the flight will be carried by that momentum. And anybody who shot a gun knows the further out you want to hit something, right? If you're over here and you want to hit something here, the more you're going to have to arc that bullet in. If you just shoot it straight, it won't do. And depending upon the kind of gun, the kind of bullet, and the distance will determine what kind of arc you actually need. And that's true of ballistic missiles as well. How far you need the missile to go, what kind of missile it is, will determine, what kind of actual flight trajectory it's going to take from launch to impact. Okay, so that's boost phase. Boost phase also is one of it is the easiest of the phases in a sense to detect, because in this phase you have a rocket that's going to be accelerating, but it means it's going to be starting from 0 and gaining speed, so it's slow in a relative sense. It's not going to be maneuvering particularly. It might have some ability to do minor course corrections, but it's not going to be able to whip around and potentially detect and evade an incoming interceptor in this phase of flight. It also creates, because its engine is burning, there's a tremendous amount of heat energy that's being kicked off, meaning that infrared sensors, particularly space-based assets that sit in orbit, will be able to detect them at that point. After that engine cuts out, yes, there will still be a thermal signature from the missile, but it will be significantly less, and depending upon where in the flight trajectory it is, that thermal image may be very hard to detect or discriminate from, say, the heat of the atmosphere that it's going through. Then you get to mid-course. So after the engine cuts out and again usually separates, the actual the rest of the weapon, the payload, will begin its mid-course phase. So at that point, it's usually exiting the atmosphere. It doesn't have to, but often it does. Especially if we're talking things like intercontinental ballistic missiles, intermediate range ballistic missiles. They're going to go up, exit the atmosphere, and come back down. This is the phase 2, where if you have not all ballistic missiles just have one warhead in them. There are some ballistic missiles that are called MIRVs, multiple independently targeted reentry vehicles. Meaning one missile could have 4 warheads, 5 warheads, 6 warheads, et cetera, et cetera, et cetera. This came into prominence in the 70s when arms reductions treaties between the Soviets and the Americans came into effect that capped the number of missiles in delivery systems, but did not cap the number of warheads. So it became a technologist's dream, right? Like, we don't need to make more missiles. What we need to do is pack them with more warheads and make those warheads as accurate as possible. The 1980s and late 70s were kind of an amazing time to be a high-tech defense contractor in the United States. Like, what a time. What a time. So anyway, multiple reentry vehicles are a thing. This is when that would occur, right? The weapon would open up, and if it's got multiple warheads, those would separate out from the bus, that's what it's called. And then they would all begin maneuvering into their own trajectories for their own targets. Sometimes they may be going after the same target, but often you would spread them out and hit multiple targets, particularly if you're doing a nuclear strike. One of the problems with nuclear target planning is that you have to account for the devastation that the warhead that goes in first is going to cause. Because if I shoot a nuke and it goes kabloom, and then I've got another one coming in right behind it, this nuke is just going to blow that one up and not create, and will do so in a way that's not going to create the desired level of destructive force. Not to mention, if you have bombers that need to go in or other means of delivery, or you have weapons that are supposed to fly past that area on their way to other targets, as this one's going up, you could lose a bunch of warheads. If you ever want to just read some insanity, go back to the PSYOP plans, Single Integrated Operation Plans, that have been declassified. PSYOP is the name for the unified plan that the United States has for the employment of nuclear weapons. And so it seeks to take all three legs of the triad, the land-based, the sea-based, and the bomber-based, and marry them all together into one concrete plan. It's pretty wild, though. Just the number of warheads that are going off in this. There were all these plans that had to do with basically nuking your way through like Eastern Europe to get through the air defense and radar defense systems so that then you could get weapons into Russia. It's wild stuff, wild stuff. Anyway, back to what we were actually talking about. So this is where you might get multiple reentry vehicles coming out. This is also when decoys would deploy. As the Soviets and the United States were developing these multiple reentry systems, and particularly as Reagan was spinning up the Star Wars program, the SDI program, there became a lot of interest in how do we incorporate countermeasures, decoys, into the system, because no matter what, the decoy is likely going to cost a lot less than the interceptor did, and a lot less than the nuclear warhead did. And so if you have a bus with, say, 5 real warheads and 5 fake warheads, well, unless you as the defender have a way to discriminate between the actual warhead and the decoy, you now have to shoot down at minimum 10 things, making this whole process more complicated. The weapon also has the ability to do a fair degree of maneuvering while it's in its mid-course phase. It can't just maneuver any old direction, but compared to the boost phase, there's a lot of maneuvering that the warhead or warheads or decoys can do. This phase of flight is one of the easier ones to detect because the boost phase, while yes, you can see it from space and it's making a lot of heat, the further away you get from the launch site because of the curvature of the Earth, the less assets you might have that can detect it, right? A radar station here on the ground is gonna look up like this, if that makes sense. And it's not gonna be able to see it launching here. But in the mid-course, it very well may be able to, using things like, big X-band radars, like the ones that have been blown up in Gulf War III, the THAAD radar systems that I've talked about that cost $300 million a pop. Those have a dual function capability. They can be angled at a high angle and kicked into very high power mode and actually look out about 3,000 kilometers. So you could have your THAAD radar there and it could look way out past the horizon into space and detect weapons coming through its mid-course phase. But it does mean you've got to have something sitting back here looking up, and it means if you're only detecting it here, you may only detect it during the second half of its flight. And with ballistic missiles, you can be talking about times, for instance, it's about 30 minutes to get an ICBM from Montana to Moscow. And the shorter the distance between the target and the launch site, the shorter that time window gets. So, ideally you want to detect it in the boost phase, but you may not, and you may have to rely on detecting it in the mid-course. Either way, let's say you did detect it in the boost phase, there is a good chance that you're still going to have to rely on other assets, not just your infrared, space-based radars and space-based satellites and systems like that. That may be just the beginning. You may have to then hand off the tracking to ground stations that are going to track it through mid-course, and then you're going to have other radar systems that have a finer. The problem with these big search and track radars, like the THAAD one, is that when they're in high power mode and they're looking very far out, yes, they can see a tremendous amount of stuff and they can see it tremendously far away. But the level of detail that they produce is insufficient to create a targeting solution. By that I mean an accurate enough lock on whatever's coming in to guide an interceptor to it. So you often have to go from some kind of usually satellite or maybe aerial-based asset that sees it in the boost phase, the ballistic missile. There are other ways you might detect it in the boost phase. For instance, let's say this was a real place, and the Navy had Arleigh Burke destroyers out here on BMD duty. Because of their proximity to launch site, there is a chance that their radars would be able to pick up the missile in its boost phase, even if it didn't see it right at launch. Ideally, you'd have multiple things seeing it throughout its flight path, right? You'd have satellites and maybe ships seeing it in the boost phase. You would have ground-based and sea-based assets detecting it in the mid-course. The United States actually operates a huge X-band radar system that's on a massive floating drilling rig. It was originally for the oil industry, for offshore oil drilling. And so it's this big ship with a nice big flat top to it with these big pontoons under it that give it tremendous stability in all kinds of sea states and conditions. Really, really nice ship handling capacity. It can just sit very still. So during times of heightened tensions, this ship can be brought out of Pearl Harbor and taken out, well, anywhere in the world, but out into the Pacific usually. And it allows the United States to deploy a very high-powered, long-range radar system, into, closer to where we think the threat will be coming from, to give us the ability to hopefully catch it in boost phase, but then also catch it and track it through mid-course and even potentially the terminal phase. And in every case, just to emphasize, you're likely to have multiple assets, multiple ISR assets, detecting and tracking and sharing that information between each other so that the missile can be seen, where it's headed can be seen. Because that's another thing too with BMD, right? Just because you see a missile launch and you can track it doesn't necessarily mean you need to shoot it down. If it's just gonna land in an empty field and you know that, then just let it hit the empty field. Okay, so mid-course carries it through re-entry, and then as it finishes re-entry, you enter the terminal phase. So this phase is when the warheads are going to be traveling at their highest velocity. They're going to likely be shrouded in tremendous amounts of heat and plasma as it's exiting the atmosphere. And it's also going to have a bit of reduced ability to maneuver. It'll have some, but as you're coming down through the atmosphere with all of that force, all of that friction, all that speed, the ability to conduct horizontal and lateral movements becomes less and less and less and less. Detecting weapons in the terminal phase, again, can be done by space. It can be done by radars right here on the ground. There's a whole series of radar systems that are designed to sit near the target that you're trying to protect, the area they're trying to protect, to look at things coming in their terminal phase. Because they can't maneuver a ton and they're generating tremendous heat and things like that, in some ways they're much more detectable than say, the boost phase, and to some degree the mid-course phase, though all that interference from re-entering the atmosphere can make it also hard to see the target that you're trying to hit, and can make it hard to get a usable target solution on it. You also have very little time at this point. Even if you can get a beautiful target lock on here and hand it off to some interceptor system, you've got very little time before it smashes in. So one of the things I want to maybe emphasize in going through this picture here is that ballistic missile defense can be thought of as an onion. You have layers of it that consist of ISR assets at each layer, the boost, mid-course, and terminal phase, that can detect, track, discriminate. Discrimination is important too. Being able to determine what is the actual thing you want to hit versus, debris or a bunch of plasma buildup from reentry or a decoy. You're going to want in your defense onion assets at every phase that can detect and track, and you're going to want assets at each phase that have a decent chance of intercepting the ballistic missile in each phase of it. And there's different kinds of interceptors that you're going to use for those different phases, and we'll get into that more in a second. But I really wanted to emphasize, what is a ballistic missile? What is its flight characteristics? What are the phases of it, and what are sort of the pros and cons, particularly from a defense standpoint, a shooting down the missile standpoint, before we went too much further, because that's super, super, super critical. Okay, sorry, I thought maybe I wasn't recording there for a second, so I wanted to double check that. Okay, moving on along. Here's some more information about ballistic missiles. I'm not going to go through all of this, but this gives you a nice little side cutout of what a ballistic missile basically is. At the front, you've got the warhead. Behind it, you're going to have some kind of guidance system that may have not just a navigation system, but usually some way to maneuver the warhead as it's traveling through mid-course and terminal phases. And then behind that, you have the propulsion system. And often you're going to have a two-phase, not always, but often two phases of boost. You're going to have one big rocket to start it off. It will come out. You'll have a smaller one, and then it will separate, and then you'll have your warhead actually in the mid-course phase. And this here kind of talks about ranges. So short-range ballistic missiles are, up to 1,000 kilometers. Medium-range ballistic missiles, 1,000 to 3,000 kilometers. Intermediate-range ballistic missiles, 3,500 to 5,500 kilometers. And then ICBMs, the big boys that we talked about at the beginning, 5,000 kilometers and above. And all of these, present their own different challenges. You can see that like an ICBM is for sure going to have an incredibly long arc to its target. And, some of these other ones may have much shorter arcs or shallower arcs. And all of them are going to maybe call for some different tactics and doctrines in order to destroy them. And here, here's some difficulties in intercepting ballistic missiles to keep in mind as we're moving forward. As I've said before, you have a very narrow window of time to detect it, track it, and then intercept it. There's a lot that has to go right in the detection phase, the discrimination phase, and then the handing off to the actual interceptor, and then the actual interceptor doing its thing is no easy feat. I mean, most of these systems are basically bullets hitting a bullet with a bullet. High velocity, tight maneuvering rooms, very little room for error. And a lot of these interceptors aren't even explosive. They're called kinetic kill vehicles, kinetic energy weapons. They're meant to just smash into the side of the incoming ballistic missile and destroy it with kinetic energy alone. We'll talk about that more in a minute, but it's insanely hard to hit a ballistic missile with another missile. And I hope that as we're going through this, you're getting a picture of how complicated, how difficult it is, how it's amazing it ever even works, giving all these things that have to come together and all these different challenges that a defender has to overcome. Here it is again, just kind of breaking it out, and you can see there's even more breakdowns of categories. Okay, we went through the phase. This one, though, I included because you can see, so this is a ballistic missile arc. As I said at the beginning, air defense is a very broad category, of which ballistic missile defense is a big component. But there are other aspects, like I said, and this gives a good sense of that. So, your ballistic missile, but then you've got your hypersonic boost glide weapon, which leaves the atmosphere and then carries on a very different kind of flight trajectory. An aero ballistic missile has a similar arc, but it stays within the atmosphere at a much shallower arc. Hypersonic cruise missiles. That's also true of non-hypersonic cruise missiles. Cruise missiles generally fly at pretty low altitude, kind of hugging the Earth. That's how they avoid detection and things like that. All of those, and then, you could add in here, manned and unmanned aircraft, drones, all kinds of other things. Satellites, right? You could add satellites into that. In fact, the SM-3 and the SM-6, I do believe, have the ability to intercept satellites, ASAT, anti-satellite weapons. in addition to ballistic missiles and other things. It's pretty risky blowing up satellites though, because you blow up enough of them and you're just going to create a huge space junk problem that, has the potential to render low Earth orbit unusable. So it's a little frowned upon to be doing that. That being said, if we ever get into a high-end, high-intensity conflict with, say, China, I am certain that we will see the employment of ASAT weapons in war, probably in quite big quantities. And, we may all lose access to space. But, when war is on, the bigger considerations can definitely get kicked out the door. So, moving on, as I've mentioned, there's multiple factors you have to consider when you're doing an intercept. What is the kind of missile you're trying to intercept? What is the kind of target you're trying to protect? Where in the flight trajectory are you trying to intercept the missile? And then another one is, what are you trying to protect and how big of an area? So over here on the left, you've got a depiction of the Golden Dome project that the Trump administration announced last year. That is essentially, Star Wars, Space Defense Initiative 2.0. A seriously high-tech, very expensive system that's meant to create a shield around the United States from any incoming ballistic missile threats. To protect the entire United States from ballistic missiles is a huge area. Before we get into any of the other components, that's just a massive area you've got to protect. So that means you need a lot of ISR equipment, you need a lot of command and control assets, you need a lot of interceptors, and you need a lot of interceptors over a large area. So it's very expensive, just on the build-out side of it. That's a lot of money you've got to allocate to protect a very large area. Compared to something, say, like Israel, right, who is likely not concerned with, who is less concerned with seriously long-range ballistic missiles, ICBMs, more concerned with the shorter range end of that spectrum. Think things like tactical ballistic missiles that are going to have, maybe a 500 kilometer or less range, things that are coming out of places like Lebanon or Gaza, up to things like intermediate range that are going to, have a bit further distance. So they don't have nearly the scope of missiles that they may need to intercept. And the ones that have the tremendously long distance, the ICBMs, they wouldn't even be expecting you to have to intercept hardly any, because they're probably not expecting an exchange with a big nuclear power like China or Russia. They would be anticipating exchange with a future Iran that possessed nuclear weapons on true ballistic missiles. And their country, Israel just isn't very big. So the number of interceptors they need, the number of interceptor sites, the amount of ISR equipment, the amount of command and control equipment they need is just significantly smaller. And you can even see here, this gives you a sense of range of the different systems. And this also is a good example of the onion approach, right? Arrow 2, Arrow 3, David Sling, Iron Dome. Those are all names for different intercept systems the Israelis actively employ in their defense. And each one of them is optimized for a different altitude band. And so that gives you that layered approach, allowing you to potentially, in a sense, it gives you 4 different levels of potential intercept. You can intercept things as they're getting closer. If Arrow 3 misses it, Arrow 2 might get a chance. Arrow 2 misses it, David Sling, all the way down to Iron Dome. And then there are going to be weapons that come in that, like Arrow 2 or 3, are just going to have nothing to do with, and it'll be left to David Sling or Iron Dome or a combination to intercept them. So that's that onion approach, and then they've just got to protect this smaller area. So it's still an expensive endeavor, but the scope of what you're trying to protect dictates a lot of the costs you're going to incur. I mean, if you just have a carrier strike group out in the ocean is a fairly small target, and it's highly maneuverable. So yes, it's still hard to protect it, and it requires a lot of effort, but it's a far easier endeavor than, say, protecting a country that you can't move, the size of Israel, or a continental power like the United States. So that's another thing you have to consider when you're talking about ballistic missile defense. Also, I'll add this too, since we're talking about, what you're trying to protect. One of the debates that always comes up with interceptors is their cost. You hear these stories of, okay, a $3 million Patriot PAC-3 interceptor took down, a $100,000 drone or a $500,000 cruise missile or something. So the economics of that are pretty skewed. if it's $3 million per intercept, but it's only $500,000 per weapon launched, you can basically get 6 weapons off for the cost of 1 interceptor. And that isn't a great, that's not great, right? And that can cause some real problems for the defending side. No matter how great your interceptors are, your radars are, your command and control systems, your training and doctrines, if you can't afford to produce interceptors in sufficient quantity and get them into field on time, who cares? And that's an important thing to think about in all of this. And there's a lot of effort going on right now to find ways to do intercepts at lower cost per shot. And while that's all important, and I think it's a totally valid thing that we've got to talk about, there is another way to think about this. And it's, what is the value of the target you're actually protecting? Yes, if you spend $3 million to take out a $500,000 cruise missile to protect, a couple of M1 Abrams tanks, that maybe, cost, not even $100 million in total. Yeah, maybe not the greatest exchange. Maybe not the greatest exchange, especially because here's the deal. The likelihood that it's going to be 1 for 1 is not great. You might have to launch multiple interceptors to get 1. And unlikely the adversary is sending just one projectile at you. So you're likely going to spend many PAC-3s to protect these 3 Abrams tanks. And yes, they're valuable, and yes, they're expensive, but if you're launching off, let's say you send 10 PAC-3 interceptors, that's $30 million you just burned that day. All right, maybe those economics aren't looking as great, especially because you could probably get in the tanks and drive them. But let's say you've got a $1 billion radar installation, say at 5th Fleet headquarters in Bahrain. Well, okay, $30 million of PAC-3 interceptors to save a $1 billion asset? That's kind of a different cost comparison, That's a different way to think about it. And, even back to the tank analogy, screw the tank analogy. Let's think of something that's, some Humvees, right? Some really cheap, low-cost equipment, right? That, yes, it's useful, but it's not very, it's not rare or boutique equipment. It's not an E3 Sentry, right? Sitting on the ground. It's not KC-135. It's not, these X-band, search and discriminate radars. So yeah, maybe using a PAC-3 on them to defend them is not worth it. But to defend a $1 billion radar installation, it just might be. And so when you hear these discussions about, it costs this much per shot to intercept, and this is what it costs on the other side to actually send the attacks, those are very valid things to compare. But we also need to look at what it is that's actually being protected. So just kind of keep that in mind as we're working through this. And that goes back also to, as you're tracking the incoming warhead, if you can figure out with certainty where it's headed, that may determine right there whether or not you intercept. You might be all ready to go and you realize that warhead is heading to some empty warehouses out on an airbase that you're not, you've evacuated already. Maybe just let them hit it. But if you realize, yeah, they're coming in and they're going to hit your X-band, $1 billion radar installation, yeah, you might need to intercept those. But you can't make that determination if you don't have really good tracking and discrimination throughout the missile and then the warhead's flight trajectory. Okay, so we've talked a lot about, the different, we've talked about the onion of defense. We've talked about some of the challenges of detecting and tracking them. We've talked about the flight trajectories and the phases of flight. Now let's talk a little bit more about the kinds of systems you could use to actually intercept a ballistic missile. So the first one up there, and that's what this guy here is. That's the hit-to-kill kinetic energy weapon that I've referenced before. There's lots of kinds like this. This isn't the only one that exists, but this is a pretty good example of what they look like. Just like with a ballistic missile where you have a missile with a rocket and then the actual warhead, interceptors are usually the same way. Your interceptor is going to shoot up, the engine's going to separate at some point, and then the actual kill vehicle will continue on using maneuvering thrusters to guide itself in and hopefully collide with the incoming warhead. Kinetic energy weapons are preferred in most cases over explosive weapons, interceptors. I mean, explosive ones do exist, but primarily what you see is these kinetic vehicles, and a big part of that is they can be lighter weight. They're a little less complicated. You don't have to have a complicated explosive system with a detonation system and safety features. You don't have the risk of some kind of accidental explosion either on the launch pad or during its flight. And particularly when you're talking about like nuclear weapons, if the less explosive energy you're imparting into it, the less risk you have of an accidental nuclear detonation or the reckless disbursement of radioactive material, right? It's going to happen no matter what, the disbursement, but just slamming into it is going to create a lot less of that than if you blow it up. So from a safety standpoint, from a technical standpoint, a cost standpoint, a weight standpoint, kinetic kill vehicles in terms of actual missile on missile intercept, hitting the bullet with the bullet, have become the predominant way of doing things. The next one would be detonate to kill, explosive energy weapon. I don't have a picture of one up here, but they're basically just like this, except they're going to use an explosive. The biggest advantage that has over a kinetic one is that it doesn't have to actually make impact with the incoming warhead. It just has to get close enough that its explosive force can take it out. That can be very tricky though, even just to get it close enough. And frankly, if you can get it close enough to blow up, it's not actually that much further to just get it to slam into the weapon. But that's the big advantage of explosives, and the interceptor types that do use explosives do so because they feel that the type of weapon they're trying to intercept is best done with something they can get close and then just. The next one's going to be directed energy weapons. Think lasers. These were really big and prominent in the 80s as an idea, as a key component of the Space Defense Initiative. There remains a lot of interest in kinetic or direct energy weapons. One of the reasons people really like them is magazine depth. If you have the PAC-3 interceptors or THAAD interceptors or whatever, they're expensive. They physically take a lot of space up. They have to be built somewhere and brought there. If you have a laser, as long as you have sufficient power generation on site, that laser essentially is an infinite magazine depth. I mean, you can just keep taking shots at incoming missile after incoming missile after incoming missile after incoming missile, which is part of why there's such an interest in developing them and fielding them. And that technology was definitely not ready in the 80s or 90s. It is becoming more mature. We're seeing more and more laser systems being introduced into the battle space. There's been a lot of interest in using them for things like drone intercepts and things like that. The big problem with kinetic energy weapons, aside from their development has yet to truly meet the hype and the desired outcomes. The other big problems you have with them though is range, right? Because it's a straight shot, you can't, angle it around or maneuver it. It's sort of like the radar system. If you've got, just imagine this at the top of the curvature of the Earth and your missile's coming up. Well, your laser interceptor might be here, and you might even be able to see this incoming warhead because you've got a satellite up here. But until it gets somewhere out here, this thing can't begin shooting at it. You also have a tremendous amount of issues with lasers going through the atmosphere. The atmosphere creates degradation of the laser and distorts it and create subtle changes to its direction, making targeting harder. You have to have mirrors and software that account for how the light's bending through the atmosphere at any given moment, which also requires a lot of good meteorological data to account for the amount of humidity in the air and particulate matter and all that. Things like clouds are a huge problem for directed energy weapons. There's also the issue of just getting enough power from point of, where the shot is taken to what it's actually trying to hit. It's hard to transfer a lot of power very far. So there's a lot of potential to directed energy weapons. There was a lot of interest in them for being space-based because you don't have the issues with having to get through the atmosphere or cloud cover in the same way. You know, you're just shooting down at things coming out of the atmosphere. So during SDI particularly, that was a big push, was can we get lasers up in space to pew, 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 pew. There's also a lot of research done on reflux interception systems, where you would have a powerful ground-based laser that would shoot up to either a plane or a satellite that was coated on the bottom with a very sophisticated mirror that would actually bounce the laser back down in a pretty wild, you know, high-tech kind of thing. Yeah, I mean, it's a crazy idea. It's very cool, I think, but it never really panned out. But that was something, that was an attempt to try to get around some of the issues that you have with the curvature of Earth and all that. Because of course too, with space, the issue you have is getting enough power up there. You're gonna put a space-based laser in orbit. You need a lot of power, a lot of heat dissipation. Far easier to build a big laser with a lot of power down here on Earth, shoot it up and then bounce it off a mirror. Or at least that was the thinking. The final kind of defense really that you're gonna see in ballistic missile defense is a point defense system. Think CWIS, close-in weapon system. That's what this guy here is. You see these on warships a lot. They're basically a big 30 millimeter, you know, rotary cannon with a radar and other optical sensors built in and a computer controlled system. So as the projectile is coming in through its terminal phase, if all else has failed, if all your other interceptors failed, as it gets very close to the ship, you can also put these on land. Whatever the target is, it can slew itself to the target, track it, and begin firing that autocannon and try to shoot it down with a hail of bullets, a wall of bullets. There are other systems in this category, but that's really the other big category of BMD defense is point defense. That is your last ditch. Everything else has failed. You know, you're really like you're praying to God at that point, because if it doesn't hit it, there's no other option. It's going into the ship or the target or whatever it is. So that's, you know, that kind of, I think, hopes give you some sense of some of the kinds of interceptors you can use and where they might be used. You know, these hit to kill vehicles are going to be primarily used, you know, in the boost phase and the terminal phase. Close in is going to be used primarily, you know, in close in support. Directed energy weapons, they could be used at any phase in the flight. You just have to be close enough to it. So, yeah. The two big ones though, kinetic energy and point defense. Okay, moving on along. So let's see. So we've talked a lot about this, but we're gonna let me, yeah, this is the picture I want. So let's talk about what it actually takes to intercept a ballistic missile, just walking it through step by step once again so that we're really clear on this. So you have the missile launch, it's in its boost phase, it's coming up, and as it comes up, you're gonna have space-based assets, maybe aerial assets that will see it, often with infrared sensors because it's kicking off all that heat. And remember, the missile is gonna be very unmaneuverable and moving very slowly. This is ideally when you would shoot the missile down, because it is the easiest to detect and it has the least ability to maneuver. It hasn't been able to separate out its warheads and decoys, so it's a bigger physical target. Can't move very fast. But the problem is it's a short window and it'll be hard to detect and it will be hard to shoot at. And so in many cases, as much as you would like to hit it in the boost phase, you're probably going to rely on more detecting it there and then handing that off to other assets that will track the missile into the mid-course. And this is where you're going to try to hit it next. And this is where a lot of interceptions are. That's the goal, is to hit them in mid-course, because you're probably going to have a good opportunity to see them, and you can destroy them with little risk of damage or injury to, you know, whatever it is you're trying to protect. I mean, if you shoot down a ballistic missile right here in the terminal phase, there's a good chance a bunch of stuff's just going to rain down on your country or your formation of troops or whatever. This is a fantastic place to hit it if you can. But as we've talked about, The target's becoming smaller. It's got a high degree of maneuverability while it's in its mid-course phase. It might have decoys. And not only, are you relying on a whole bunch of assets to track it, but you've got to get a missile all the way from here to somewhere in here and to hit it. The THAAD interceptors, I got a picture of these down a little further. They're meant to do out-of-atmosphere interceptions. And there's been some really amazing footage coming out of Gulf War III of what these explosives look like from Earth, because you can see them up there. And then you're going to come down into the terminal phase. You're going to have a lot of equipment that's going to be able to see this, right? Because presumably, the base or the town or city or whatever that you're trying to protect has a lot of air defenses built up around it. So you're going to be able to put a lot of electronic eyes on it and probably get a pretty good target solution. Though, as I've said, because it's coming out of the atmosphere, there's going to be a lot of plasma and heat around it that's going to make it harder to detect it. The flip side of that, though, is it means that the warhead itself has a hard time detecting what it's heading towards. In an ideal scenario, your warhead would enter the atmosphere and then pop open some sort of, camera or radar system that could then look around and see what it's trying to, what's there and if it's actually on target. Like, let's say you're trying to use a ballistic missile to hit an aircraft carrier. Because an aircraft carrier can move. As the warhead comes down, you might want to be able to look around and say, oh, the carrier's not here where I thought it was. It's actually, it's over there, and try to re-angle. It's hard to maneuver at those velocities with all that pressure and force. It also, the sensor that you're going to put on the front of that warhead is going to have a very hard time looking through all that interference and actually seeing anything clearly enough to lock onto. So that's a big challenge for missile designers. And the Chinese have been pouring a lot of effort into this because they have some very well-known, is it the DF-21s? Maybe it's the 27s? Long-range ballistic missiles designed specifically to take out US carriers and other warships at sea. And a key component of that is being able to maneuver during the terminal phase and actually see something in the terminal phase. So, both sides have similar kinds of issues, right? In detecting the target, tracking the target, staying on target. Obviously, if you're just trying to lob a ballistic missile, into a static building or a nuclear weapon into one where you don't need perfect accuracy, the demands on the attacker go down. But if you're trying to be more precise, like you want to put a ballistic missile into a specific building and it's a conventional warhead on an airbase, or you want to put one into a carrier, you're facing a lot of the similar challenges. If you're thinking about a carrier, right? You have to, just like when you're trying to detect the ballistic missile as the defender, the offender has to find the carrier and track it. And that could be very difficult because, again, the carrier moves and the ocean is vast. So both sides have a lot of the same kinds of challenges, and the defender in some ways has an easier time, but depending on what they're doing, it may be almost just as challenging for them as the defender. But this is how it works. The missile launches, it gets tracked, it gets discriminated, and then that information is handed off to more sophisticated, narrower scoped radars that can actually track it in, and then that's handed off to interceptors that then loft out, especially if they're missile-based ones, that will then use a combination of telemetry from all these other ISR assets and its own internal seeker head to knock out the warhead. It's an insanely complex process, and I hope I've emphasized that here today. Let's see, I wanted to show you. Oh yeah, so this is a representation of a THAAD seeker actually going out. So this would be the incoming warhead that we're trying to shoot down. This is the THAAD interceptor. This is its infrared search and track system. So it's using an infrared system to look out and see the heat signature. And then it's using these thrusters to maneuver itself into a collision course. And if you can just imagine this, you're in space, you're traveling incredibly fast, and you've got to hit this thing, which is also traveling incredibly fast and is not very big. And all of this has to be tracked, discriminated, and shot down in this insanely tight time window. Here's some other kinds of interceptors. So this is an SM-6. This is a missile that you can launch from, say, an Arleigh Burke out of a VLS system we talked about last time, vertical launch. And it can hit targets in a wide range of altitude bands, all the way out to out of atmosphere interceptions. Here's one of the well-known nowadays THAAD batteries. This is just the launcher. You can't see the command truck or the radar in it, but that's an actual interceptor going up. And then these are pictures of THAAD intercepts in space. These are things being blown up by kinetic force over Israel during this war. And that is just, I just think that's such a mind-blowing thing to see. I've never seen something quite like that in person, obviously. And there are pictures from tests that have been done, but we've gotten so many of these now because so much of this is going on. And the fact that this works at all is insane to me. And that's a big thing I want to emphasize too in this video, is that when we discuss, BMD, ballistic missile defense, there's a lot of things you need to consider. Cost, what it is you're trying to protect, what it is you're trying to protect against, what kinds of ISR assets do you have, all of that stuff. But the one thing to really keep in mind is it's a very difficult thing to do. And while I don't think we shouldn't hold, the military and defense contractors to a high standard for these kinds of things, we also need to be realistic that it's an incredibly difficult process and no system will be 100% successful at intercepts all the time. There will always be what's called leakers, meaning a warhead that got through and hit its target. So when we're building out these systems, when we're fielding these systems, when we're talking about these systems, we need to remember how complex it is. We need to remember that it's never going to be perfect. And we need to remember that there's always got to be a balance between what is the cost of the thing you're trying to protect, what is the cost of the actual intercept, and what is the cost of the thing being launched at said target. And ideally, you have a well-designed onion of defense systems so that you rely on a wide variety of ISR assets, space-based, aerial-based, sea-based, ground-based, all working together and linked together. And that's a big part of it too. You could imagine a nation that has super slick intercept missiles and launchers, super slick space-based ISR, super slick ground-based radar, tracking and discrimination radars, fire control radars, all of that, but lacks the ability to integrate all that into a complete picture. If you don't have that complete picture and it's not being made in real time and updated in real time from all these different sensors, you're almost certainly not going to be able to make a successful use. All of these things have to talk together. They have to talk together in real time, and they have to talk together reliably. And so an adversary who's smart actually may systematically take out nodes in that ISR system, nodes in that command and control system, nodes in that communication system, so that even though maybe the bulk of the intercept system overall remains intact, enough of the nodes in it have been degraded so that the system can't communicate with itself. And there's evidence that Iran has been doing some of that. When you look at some of the targets they hit, back when things were really popping off, they were hitting, radars on THAAD missile batteries. They were hitting big X-band radars at Fifth Fleet headquarters, and other things like that throughout the Gulf region. All of those were meant to poke holes in the system's vision and thus make it harder to get the correct picture of the battle space and thus successfully track the missile and then intercept it. So the Iranians, were doing some of that. And, when we were attacking Iran, we did similar things. We went in and systematically took out nodes within their ISR and C2 systems to make it so that even if you didn't get every weapon, their ability to talk to each other and thus work together in a joint way has been diminished to the point that it's now just kind of individual components doing individual things. And that's really never going to work if you're trying to intercept a ballistic. You might be able to do that, like with a theater ballistic missile maybe, where you were going to have so little time anyway, you know, because the distance between launch and target is so limited. But that's another one of the big complexities. And when you look at the Israeli systems, when you look at the integrated systems that the United States has throughout the Gulf region and is integrated with its allies, it is an incredibly impressive array of systems that work together imperfectly, 100%, but work together way better than one might think, especially when they realize the complexity and challenges of this. There's also this is not going away. The interest in interceptors and the ability to shoot down ballistic missiles and to conduct anti-air operations across the full range of both altitude bands and aerial threats, drones, manned aircraft, etc. I mean, that's not going anywhere. There's more interest in it than ever. And the technology is at a point where it actually does work. You know, that was the problem back in the 80s. The technology just didn't work. A lot of great ideas, a lot of really fun ideas, it was so wild, the ideas. The technology wasn't there. It is there now to make it work. And there is going to be ongoing efforts by militaries around the world to make systems better from a detection standpoint, from a command and control standpoint, from a communication standpoint, from an actual intercept standpoint. A lot of effort to give more varieties of interceptors for different kinds of targets. I mean, yes, you don't want to be shooting $3 million PAC-3s at $5,000 drones that are swarming you. Like, that's definitely not what you want to do. So there's a lot of effort to broaden the scope of the ways in which and the weapon systems in which we can intercept missiles. That's not going away. But of course, on the other side, people who make ballistic missiles and other aerial assets, jets, drones, etc., cruise missiles, are doing a lot of work to make it harder to hit them. And so as with any evolution in military technology or doctrine, you see the constant back and forth, right? The enemy, that's the saying, the enemy always gets a vote. So you come up with a really slick way to intercept a missile, the enemy is going to come up with a way to get around that. You know, decoys was an example. The Iranians, this is a pretty clever way. The Iranians were having trouble getting their ballistic missiles through US and Israeli air defenses over Israel. So the Iranians started putting cluster munitions in their ballistic missiles, so that as the ballistic missile was coming through its mid-course and into its terminal phase, it would open up and lots of little bomblets would come out. And now, yeah, maybe you do hit the main warhead, you know, the main, the missile, but it's probably already disgorged all of its little bomblets or most of it. And now you could have dozens, if not hundreds of little bomblets raining down that you probably can detect and track, but are gonna have a very hard time shooting down. Cluster munitions have their limitations. You know, they're wide area weapons, so they're gonna spread out, so they may not hit exactly what you wanted to hit. Because they're small little bomblets, they don't have tremendous destructive force. So again, depending upon what you're trying to hit, that may not work. And they also have a tendency, like landmines, to, you know, stick around for a very long time. You know, not every bomblet is actually going to detonate the way it's supposed to, and they may sit there in rubble or under the dirt for many, many years, and then down the road, you know, some kid comes along and digs up with it and blows up. So that's another issue with cluster munitions. But if you're just trying to rain, you know, fear and terror and destruction down over, you know, civilian infrastructure and population centers, or say like air bases or things like that, and really the bigger thing is just causing that constant fear and chaos, not necessarily the level of destruction. This innovation by the Iranians is fucking brilliant, frankly, and has proven very effective at getting through the Iron Dome, David's Arrow integrated air defense system that the Israelis have, which is a very slick system and works very, very well. All right, I think that might be it for today. As I said, this is the first of probably 2 to 3 videos. And the next video will probably be a discussion of the different kinds of air defense beyond ballistic missile defense that exists. And then we'll do a third video that gets more into the weeds about cost of these different systems, maybe a bit more of the history. particularly some of the early history back in the 50s and 60s with the Nike Zeus program here in the United States. Back then it was called ABM, Anti-Ballistic Missile. Now it's called EDM, Ballistic Missile Defense. And sort of looking at the future of all of this. But I wanted to start here as a primer because BMD is a very complicated process in the way in which you successfully intercept a ballistic missile. The systems, concepts, doctrines will have broad application through all air defense that we're going to talk about. So I hope you've enjoyed this. I'm going to get back to regular Gulf War III coverage probably next week. Admittedly, not a lot's been happening out there in a sense. It's just, contested. Everybody's just spinning their wheels in Pakistan, not getting anything done at the negotiating table, et cetera, et cetera. So we'll get back to that soon enough. But thanks for joining me today. I hope you've enjoyed it. I certainly have. And remember, shooting down a ballistic missile is no easy task. And when we talk about these things, and you read articles about these things, do keep in mind the difficulty, the complexity, and the nuances that we've talked about today. Because it's not as clear cut as interceptors work, interceptors don't work, or interceptors are too expensive, or anything like that. It's way more complicated. All right. Reach for the lasers, and as always, embrace those motherfucking lights, y'all. See you next time. Okay.